Okay, great. So next up we have Nils from SRS. He is our he is the person responsible for DevOps, customer integrations, and QA testing within SRS. So he's been with us for 3 years. When I first joined SRS, Nils was an intern, and then about a year later he was working with us. So it's been great. So I'm going to hand over to him now, and that's it. Okay, you can use this if you want, or
yeah. Should I?
Yeah, sure.
Okay. All right. I just have to adjust this here. Can I? Yeah. Can I make this a little bit bigger? Oh well. Never mind. Yeah. All right. Hello everyone. My name is Nils. Today I'm going to talk about srsRAN project on Kubernetes. As Brandon said, I joined SRS 3 years ago. I studied IT security before, and I'm mainly doing DevOps, hypervisors like Proxmox and VMware, Kubernetes, performance tuning on ARM, Intel, and AMD, and some system administration. I also do the same work for customers. And if I have a little bit more time, I also do the quality assurance and testing. So what is this presentation about today? You can deploy srsRAN in very different scenarios. And today I want to show you how to do this on a minimal R&D deployment. I'm going to start from zero. So we're going to look a little bit into the node configuration. Then how to actually deploy the Helm charts. And in the end, I'm going to show a little bit like tricks for debugging and monitoring srsRAN projects. So first of all, the configuration. This is what we are looking at. So we have, of course, the srsRAN gnode B. Then we're going to deploy Open5GS, Linux BTP, and some monitoring tools like Grafana. We're going to work on a 7950X, 16 core actually. There's a typo in my slides. 64 gigabytes of RAM, an Intel E810. It's a specific version which can operate as a PTP Grandmaster. As you can see in the graphic, there is no external PTP Grandmaster needed in this setup. This configuration is called LLSC1. And yeah, we're going to use Ubuntu out of convenience. And in this setup, you could, if you want to run up to 3 cells. Yeah, all right. So first thing, why are we doing this? It's like the tuning of the system or maxing out performance is usually cheaper than just buying a new CPU which has 64 cores or whatever. But it also makes tests repeatable. So in case you want to run tests over 48 hours, for example, and every night at 1 a.m. the unattended upgrade starts to kick in, you will mess up the test results, and this is actually not something that you could repeat and expect the same results. But it also helps to stabilize the system, and yeah. So how do we going to do this? We're going to use the real-time kernel of Ubuntu. We will look a little bit into CPU isolation and core pinning if we get there. The static CPU manager of Kubernetes. And then we look a little bit at DPDK and systemd slicing. So first of all, installing the real-time kernel is a fairly easy thing. You can do it over apt, sudo apt install Linux realtime, or you can go over the pro subscription of Ubuntu. Both is actually the same version, so up to you what you want to do. You don't have to use Ubuntu, so you could also use Red Hat, SUSE, which also show good results with the real-time kernel. But we use Ubuntu because we test it the most in our labs. The second part is I actually advise to tune the BIOS. This always depends on the server that you have. So Dell and Supermicro have different guides on tuning their systems, so you have to look into this. Maybe if you use a workstation PC, this will be a little bit different. But in general, I advise to set the BIOS to performance in order to get the maximum performance out of the system. And another thing, which probably doesn't apply much to servers, but more to workstations, is that I would always disable all of the devices that you don't need, like a Bluetooth, a sound card, for example, because all of these devices use hardware interrupts, which in the end could interrupt the G-Node B or could slow down the system. So what we want to do there is we want to take everything out of the system that could, in theory, slow it down, and yeah, we don't need it. We don't need Bluetooth on a CUDU server. Yeah, so CPU isolation. The general idea here is to separate the CPU cores that we have in at least two groups. One group is responsible for basically the operating system, running hardware interrupts, running systemd units, services, and all of the operating system processes. This is usually the smaller group, which should be, if you can, one or two cores of the system. Because, well, the less cores you give it, the less responsible it is. But usually, in this scenario, we don't care much about responsibility of the system in terms of that the screen is working fast. We want the CU and the DU to have the most resources. So usually what we do here is we choose a single core for the housekeeping, and the remaining cores go into the isolation CPU group. Another thing, or like, how do we do this? So as far as I'm aware, there are two ways of doing this. You could either use isol CPUs, which is easy to set up, but static, so if you want to change it, you will have to reboot the system. But you could also use C groups. It's much more difficult to set up, but you are more flexible. So for the beginners, I would definitely recommend using isol CPUs. Okay, so now we need to create these groups. And there are some considerations that we have to do or to make in order not to mess up. The first thing is that specifically for our software, we've seen that hyperthreading gives us a better performance, even though a lot of tuning guides recommend not to use hyperthreading. So when you have hyperthreading activated and you want to separate the CPU cores into two groups, into the housekeeping and the isolation CPU groups, you have to make sure that if you choose, for example, core 0, so if you have hyperthreading activated, you have a logical core and a physical core, and both share their cache memory. And you don't want the hyperthreading core in the isolated CPU group, for example, and the physical core in the housekeeping, because both share the same memory, and in case there is a high load, it could be that you create cache misses or that you actually overload the CPU core, which then leads to lates in the DU, for example. And we want to avoid this at all costs. So to create these groups, what I usually do is I go to lsCPU -p, as you can see in the graphic. And on the very end, I don't know if you can see, is there? No, well, never mind. The first core ID number 0, you can see is using L1 and L2 of core 0, and the core 16 is using the same. So these two cores, core 0 and core 16, need to go into the same isolation CPU group, or in the housekeeping in this sense. And for the isolated cores, we're going to choose all of the remaining cores. If you have NUMA nodes, for example, you don't want to create these groups consisting of cores from different NUMA nodes. The reason is similar to the hyperthreading. It's just better to not mix them. So I also recommend there to not cross NUMA nodes. But what you can, for example, do is create the housekeeping in NUMA node 0 and the isolation CPU group in NUMA node 1, if you want so. The same for dual socket systems. So if you have a system running 2 CPUs, I would always recommend to create the isolated CPU cores on a single physical CPU, and the housekeeping may be on the other or both on the same, but don't mix the 2 CPUs in those groups. Yeah, okay, the next step would be isolating the cores over a group, for example. I think this could be another presentation. So I don't have 1.5 hours today, so but I found this great blog post on the Ubuntu blog, which explains perfectly fine how to isolate cores using isol CPUs. So in case you want to do that, I recommend this specific blog post. The next step, so I assume now that we have isolated the CPU cores. You've done the tutorial that I mentioned before. The next step would be configuring Kubernetes. Usually Kubernetes deploys the workloads on all available cores. And it sets a so-called CFS quota to, I think default is 80%, in order not to overwhelm the system. Because if you deploy something on a CPU using all cores, and you also have the system running there, you could run into a situation where the system just crashes because it doesn't have enough resources anymore available. But since we move the system and all of its processes to the housekeeping group, we don't have to care about this anymore. And it would decrease performance if in the isolated CPU groups we would use this CFS quota. So I always recommend to disable this. And then in order to, so Kubernetes needs to understand what is the housekeeping group and what is the isolated CPU group. And this is possible by using the static configuration of the CPU manager, which also allows us to give exclusive cores to workloads. For this configuration, it's important that you define or that you tell Kubernetes which are the CPUs reserved for the system, which is done by the reserved system CPU parameter here, 016, like the housekeeping group. And then, because we have hyperthreading activated, we want Kubernetes to always choose pairs as we did before. So we don't want to deploy workloads on cores that not belong together in terms of hyperthreading. And this is done by the full pCPUs only parameter here in this config snippet. And then in order to deploy always on the same, in order to get these exclusive cores, you have to use the QoS class guaranteed, where you have to set requests and limits to an equal value. And you always have to choose an even number of cores due to the hyperthreading. Then I want to just introduce DPDK. So it's a set of libraries that enables high-performance packet processing by bypassing the kernel. I don't know if you have tried it, but if you have tried it, you maybe realize that if you bind an interface to this driver, it disappears from the kernel. So you cannot use it anymore for PTP. And, but this is what we want to do actually. So we have to use srIOV, which enables us to spawn a virtual interface on the physical port, which we then can bind to DPDK and use this. So for the receiver in the end, it will be transparent. The receiver will not know if we've used a virtual function or not, but using the virtual function, we can actually bind it to a DPDK compatible driver. So this was the node configuration, and now we go into the deployment. As I said before, we deploy the Gnode B, we deploy the Grafana Web UI, we deploy the Linux PTP as a grandmaster, and in the end, if we have enough time, I'm going to show a little bit a nice tool which is called RU Emulator, but we're going to come to this later. And I chose Open5JS for this deployment. It's a core network that I like to use. It's easy to configure, and there are also Helm charts available, not from us, but from Gradient actually. So before deploying anything in Kubernetes, you need to have Docker images. We provide Docker images for Split 8 and Split 7.2 with AVX 512 and AVX2. You can find them on our public Docker Hub repository. Yeah, and we also include images for Grafana, for Linux PTP, for the RU emulator, and for some more we provide other images as well, which we don't use here now, but you can have a look if you want. All of the Docker files are available on GitHub, so you can also build the images yourself. And this is also something that I wanted to show because I've stumbled over this like some time ago. If you build directly into the K8s.io namespace, you don't have to upload the image to a Docker registry and then download it. You can directly use it in your Helm chart if you set the image pull policy correctly. And if you, for example, want to change the Gnode B image by adding new tools, by maybe changing the code, we recommend that you use the assert level minimal and that you also enable DPDK for high performance. Deploying Open5JS is a straightforward process. But it's important that you note down the PLMN tracking area code and the slicing information that you're using in order to connect the Gnode B, because this is also something I get wrong a lot of times, and then I have to update my config and upgrade the deployment again. To avoid this, note it down and make sure it matches the Gnode B configuration. On the right here, you can see an example or like a snippet out of the Open5JS values YAML. It's not complete, but it includes most of the parts. And for the Open5JS, you also have to create a persistent volume. The Kubernetes gurus under you have maybe spotted the host path. I know it's not the best way, but it's a convenient way to deploy it in a single node cluster. If you don't want to use something easy like this, you can also use every other PV provider that you can or want to set up. The next part is PTP. And I've heard a lot of questions about PTP, and I think it's also something that can go wrong. So if DU and RU are not synchronized properly, they cannot talk to each other. So it's really important that you get the PTP set up right and that it's working properly. So this is something that I would pay attention to make sure that all of this is working. I always recommend to test this first either in a bare metal setup with the RU, so you know everything's working, and then you move to Kubernetes. If you don't have access to the node, you can also deploy like a pod with the same image and then test from inside that pod. We use the LLSC1 configuration in this scenario. Here, you have like an example config for Linux BTP for this scenario. You can use TS2PHC in order to sync to GPS if you want to. But with the NIC that we are using, that we are also using in the SRS kit, you don't have to actually have PTP, which is very convenient sometimes if you are in a building like this. We had a workshop last year and we couldn't get GPS signal, so we couldn't do a demo because RU and DU could not really communicate. Yeah, then there are some probes which monitor the healthiness, the liveness, and the startup of the container. And yeah, something else that I've discovered is when the system is under high load, maybe the PTP doesn't get enough CPU time, and maybe you get like some deviation from the regular, or like it degrades the PTP signal. And what I recommend here is to also use QoS guaranteed for the Linux PTP. A single core is enough. If you have it, I would definitely use it. Okay, so the next part is the deployment of the radio unit. This really depends on the unit that you have. All of them are usually quite different, and it's a really challenging topic. Yeah, the general approach here, or my general approach to this problem is, first of all, get console access, set it up properly, make sure some of them get really hot, so make sure they are ventilated well and don't overheat. Then get SSH access to configure the RU config. Something that is very important is the DU MAC, for example. If you don't get this right, maybe the data is received by the RU, but not really, it doesn't work with it. So make sure the DU MAC is correctly configured, PTP is set up correctly, then the bandwidth and compression are also something that are important for the first attach. If this is not correct, the G0B and the RU will not be able to talk to each other. The next step after you've set up the config is to make sure that PTP synchronizes correctly. After that, you have to make sure that the RU initializes properly. Some vendors or some models do this by themselves. Some others need you to do it manually. And after that, I would attach a DU and then monitor the KPIs. It's very important that when you've attached the DU and don't do traffic, that you don't see any early or late packets. If this is the case, usually there is something wrong. And if there is something wrong in the beginning, trust me, you will have, it's a nightmare to debug this in a later stage. So make sure no early or late packets, the KPIs are clean, the traffic is received, and then you can proceed to the next step. So in order to deploy the G0B, yeah, this is also something that is a tough job. The first part is always to create a working config file. We have the node set up correctly, and now we need to make sure that the G0B or the DU is actually connecting to the RU. I always recommend in the beginning, don't start with 4x4, 100 megahertz. This doesn't make sense. It has a lot of curl pits where stuff can go wrong, so choose maybe 20 megahertz, single antenna, no DPDK, BFP9, something that is easy to configure and doesn't give much of potential errors. Once you have a working config and you've attached the G0B to the RU, you can increase bandwidth, you can start using DPDK, and you can also use core pinning in case you want to really max out the system. It's always important to monitor the KPIs, because again, if you see lates and earlies, the connection is not stable, and this will at some point be a big problem. The typical errors that I do myself are, for example, setting wrong MAC address in RU or DU. Both need to be aware of the MAC address of each other. If this is not set correctly, those two guys are not talking to each other. Sometimes when I'm integrating with a lot of RUs, I have to really make sure that all of them have the same firmware. If not, this can also be a problem. Wrong VLAN configurations in the switch, for example, if you use a switch, but also in a LLSC1 configuration, this can be a problem. And yeah, the G-Node-B not connecting to the core due to wrong PLMN, wrong TAC, or wrong slicing information. You can always use the dry run of Helm to render the configs and see what you're actually getting, and if you want to check before the deployment. And what I was talking before about is you can use also a dedicated pod. Sometimes you don't have access to the node. Maybe you don't want to install all of the dependencies for srsRAN. So take the Docker image, deploy it, but don't start the G-Node-B right away. Put in like a command, like a while loop, which just sleeps every 30 seconds in order to not kill the pods. And then in there, you can run the G-Node-B and you can test your configs. As soon as you have the config, you can just remove this and add the entry point again. Okay, then some considerations for the configuration of the Helm chart. So depending on where you get your image from, you have to set the image and the image pool secrets correctly. As I said before, it's very convenient sometimes to just build the image yourself on the system. Then something else, which we will change in the future, but you have to use it right now, is the host network needs to be set to true, and we need to use privileged containers. This is because I haven't implemented yet support for an sriOV provider. Yeah, some parts of the Helm chart don't work if you use or if you change this. But as I said, we will change this in the next updates, so we can get rid of this and you can configure it differently. Then I would always use QoS guaranteed in order to get exclusive cores for the G-Node-B. And yeah, in the resources, you eventually have to set huge pages in case you want to use DPDK. So huge pages are necessary for DPDK. Yeah, and then summing this up, we have 2 cores for the operating system, for the housekeeping group. Then we have 2 cores for Kubernetes. Usually Kubernetes deploys infrastructure pods like the CNI, the DNS, and so on, and they also need a little bit of CPU time, so we reserve 2 cores for Kubernetes. Then, as I said before, 2 cores for PTP. Then I would give like around 4 cores to Open5JS and about 22 cores to the G-Node-B in this specific scenario. Of course, if you have a smaller system, you can reduce this. You don't have to give 2 cores to PTP for L or, yeah, so it's just for this example, but you can tinker a little bit with it and see what you get. Once we have the deployment, we need to actually monitor it. And one thing that I think is really cool, I also really like the logo, is K8s. I don't know if you heard of it. It's a command line tool which facilitates a little bit the usage of kubectl. You can, of course, use kubectl if you know what you're doing. Then I also always recommend to check the G-Node-B logs that the G-Node-B generates, check if you have warnings. So this is the same as running bare metal. You have to check for all sorts of warnings, errors, and so on. If you want to have it a little bit more convenient, I can recommend the K8s dashboard, which you can access over the browser. And there's also the srsRAN Grafana, which you can deploy via Helm in order to monitor the KPIs of the G-Node-B. So the srsRAN Grafana consists of 3 components. It's the metric server, the InfluxDB, and the Grafana dashboard. The G-Node-B needs to send its metrics to the metric server. This is what you see here on the top. This is what you need to configure in order to make the G-Node-B send those metrics. And then, you can adjust the values in the Helm chart. But I would say it's all pre-configured. The only thing that you need to adjust is the cluster domain which in this case is cluster.local. So you need to adjust this and set it to whatever you have set in your cluster. And from there, you should be good to go. You can just deploy and use it. And one thing, don't change the UID of the Grafana dashboard or the Grafana data sources, because otherwise the dashboard won't work anymore. Everything else you can change, but you don't have to. And yeah, this is how it looks. If you're interested, you can also have a look at the srsKit demonstration, where we also use the same dashboard, not in Kubernetes, but yeah, it's exactly the same. So then the next step would be maxing out performance. The first step I would do on the node is to configure DPDK. As I said before, we need to use sriov. And to create a virtual function, you have those 3 commands here, which you can use. But this is also very specific to the specific network card that we are using here. So it gives you an idea, but you have to adjust it a little bit. If you want to know how this works, you can, I think in the DPDK documentation, you find everything you need. Something else that I also, or that I've stumbled about in the past, is that first of all, sriov needs to be supported by the hardware, but also IOMMU needs to be supported if you want to use the VFIO PCI driver. In case you come across tutorials that explain how to do this and so on, and you cannot use VFIO PCI because IOMMU is not enabled or available, you could use IGB UIO, which is performance-wise the same driver, but it doesn't have any security features, which probably doesn't matter. Depends on the deployment that you're planning. And then the interesting part. So maxing out the performance by using CPU pinning. A single cell usually doesn't need it if the CPU is big enough. So in this scenario, I'm gonna show how to isolate or pin 2 cells, or do CPU pinning for 2 cells. The first very important thing to consider is that the L2 cell CPU's thread needs its own core, and it cannot share this with anything else. So you need to make sure that this thread or this group gets its own core. You can see it here. It's running on 2 and 14 and 7 and 19. Yeah, then maybe you've used this section before and you've used the isolated CPUs parameter. I recommend not to use it because it creates C groups. This messes with the Kubernetes configuration. And yeah, you basically don't need to use it. So leave this one out. And yeah, then apart from that, so the amount of downlink and uplink threads, for example, really depend on what you want to do in the end and what you want to achieve with your deployment. Depends on your bandwidth, depends on the amount of users, and so on. So for this is usually something that we do for our enterprise customers. It's something that you have to get familiar with and yeah, walk yourself through it. What does these threads do? How do they work? And what do I actually need? It's impossible to give you like a concrete answer and say, okay, this is the setup that you want to use. So it's more like a trial and error process. For this trial and error process, I really like to use the test modes. It simulates OFH, PHY, and MAC. And what it does is it simulates it by attaching a fake UE or multiple fake UEs you can choose. And yeah, makes them do traffic basically. This way, you're gonna see if the system is actually capable of running these workloads under these conditions with your isolation settings. If you start seeing lates, for example, or warnings in the config, you know, okay, I have to maybe change something. Maybe I'm going too high. Maybe it's too much traffic, too many users. As an example, the best we've tested with this, for example, was on a AMD 8400P, 64 cores. We were able to run 12 cells with 800 users connected, so 9,600 users in total, without any lates, warnings, or whatever. But this really requires you to set the affinities and the threads and so on perfect. So it took a long time to get there. And the last part is to configure the HAL arcs, which are responsible for DPDK. These are the cores that DPDK uses. And I usually set them to the same as the RU CPUs, which are the CPUs which are not super important for the whole deployment. So there can be interrupts from DPDK. Yeah, but this is also something to be determined by you. And the last thing I want to show you is the RU emulator. So we developed a tool that, as the name says, emulates an RU. I see it useful in two scenarios. You could first of all test your infrastructure. In this scenario, it might not make too much sense, but if you deploy it in a bigger network, if you want to check if the latency of the switch network that you have is working well, you could just deploy it, connect the DU, and check the KPIs on both sides if the traffic is coming through, if there are any drops on the way. This would be the first scenario. The second scenario where I see it is if you have a switch in between which supports port mirroring, you can mirror the port of the RU and send the traffic to both, to the RU emulator and also to the RU itself. And then you can check, because we had an issue recently where the RU was not receiving all packets, but on the way we were tracking and we could see that the packets were actually sent towards the RU by the switch. We just didn't know exactly what is it sending. So what we did is we deployed the RU emulator on a different machine, made both ends receive the same traffic, and then realized that there is some corruption because the SFP module was actually not working well on the way towards the RU. But between the DU and the switch, everything was fine. So this is another way of like debugging your deployments. I'm sure you can find other ways of deploying the RU emulator. It's just something that I wanted to show to mention it here. What are the next steps? So the next steps would be adding a load balancer for N2, N3, and F1, add support for the srIOV provider so we can get rid of the privileged container and also get rid of the host network. We want to separate the Helm charts into two, so you can deploy CU and DU in two different scenarios or in two different pods. Then we want to integrate more support for the static CPU manager, and also we want to update the Helm charts with every srsRAN project release. Currently, we are a little bit behind. The preparation for the workshop was tough, so I didn't have time to update everything before this. But in the future, we want to have some pipelines that do this automatically. And the last one would be some RU emulator improvements to have more statistics, to have a better overview of what we are actually sending and receiving. That's it so far. Thanks for your attention and feel free to ask questions.
Is this information available online in the documentation?
We have, I'm not exactly sure. We have documentation about Kubernetes on, srsRAN on Kubernetes. But I think we are a little bit behind updating this. So probably in the next 2 weeks, we will update this, and then you will see exactly what I've presented here in the docs.
What can you do with the RU emulator as of now?
What can you do with the RU emulator as of now? So you can, what it does basically is it receives traffic and sends back random IQ samples, just to make or to simulate an RU, which has some UEs connected, but yeah, nothing real. In the future, we want to add more statistics, so you can actually see if the RU and the DU are in sync, which is currently not working. We want to have some statistics on the packets that we receive. This is something that you have to track by yourself currently on the system. So it's still in a very early stage, but I think in the next weeks or months we will improve this.
Does using isolated CPUs core pinning help if not for Kubernetes container?
Yeah. Okay. Yeah. Good question. So you can use the same isolation principles that I've used here also for if you want to use Docker or Podman. Yeah, it's the same. You can do it exactly the same. You just need to make sure that the Docker container picks up the right cores.
When we are not using Docker container running on bare system,
Yeah.
so does using core isolated CPUs help with that?
You mean the config parameter isolated CPUs?
Core isolation.
Core isolation helps, yeah, definitely. So we also do this on all bare metal deployments. And yeah, I would definitely say it helps. I would say CPU isolation is always a good thing. Core pinning depends on you, if you are familiar with what you are doing there, because if you do this wrong, you can mess it up. And then the G-Node B is running way worse than if you wouldn't use it. But yeah, I think we also have a tutorial on this on bare metal in the docs. So if you want to have a look there, I'm sure you can find some information there.
Any more questions for Nils? We have 6 minutes.
All right. Thanks a lot for your attention.